Welcome to Unique Academy YouTube channel. So in this video, we will see gate problems from thermodynamics. So first question. So a heat engine extract heat from a thermal reservoir of temperature 1000 Kelvin. Let's say you have a heat engine. It is taking a heat from a source, which is at 1000 Kelvin. So takes a heat, QH. So it's a heat engine. So it produces work output and rejects heat to a reservoir which is at 100 Kelvin. So you have QH, QL, and W. So what is the combination of this QH, QL, and W? This heat engine is allowed. We know that the work output is QH minus QL. So now if you look at the A, if you look at A, your QH minus QL is 500. So the answer A is wrong. QH minus QL will be 1500 for A, but what is given is 1000. Okay, so that is wrong. The second one, QH minus QL is W. So your W is equal to QH minus QL. So this will be equal to QH minus QL. So it will be right. And now if you look at C, again it will be right. So this also will be equal to QH minus QL, 5500. So this is also right. So D, QH minus QL is 5400. So it is not correct. So there will be two answers. So which you will be choosing it? So now what you are doing is you are trying to find out. So by your energy conservation, the two answers are matching. From your energy conservation, these two answers are matching. From the entropy point of view, if you look at, you take this entire system as the universe. Maybe if you take this entire system as the universe. So what is the entropy change of the universe? Entropy change of the universe is greater than or equal to 0. So entropy change of universe is greater than 0 for irreversible engine. Entropy change of universe equal to 0 for reversible engine. Now let us check from the entropy change point of view for this answer B and C. For B, so if you look at B, the entropy change of the universe. First is the reservoir 1. So you have reservoir 1 and there is a reservoir 2, then there is a cycle that we will be taking as 3. There are 3 systems inside the universe. One is reservoir 1, that is the high temperature thermal reservoir. Reservoir 2 is the low temperature thermal reservoir and the heat engine. And now the entropy change of the universe will be equal to entropy change of 1, system 2 plus system 3. So entropy change for 1. So the 1 is losing entropy because the thermal reservoir, 1000 Kelvin thermal reservoir is losing entropy because it is losing the heat. For a thermal reservoir, the entropy change will be Q by H, maybe QH by the temperature, TH. So maybe we will take this as this temperature as TH, this temperature as TL. And since it is losing the entropy, negative sign, minus. And entropy change of the system 2, this thermal reservoir 2, 100 Kelvin is receiving heat. So entropy change will be positive. So it will be QL by TL. Entropy change for 3 cycle will be 0 because entropy change for a cycle will be always 0. Entropy change for a cycle will be always 0 because entropy is a property. So entropy change for the cycle will be 0. Now let's substitute all the values. QH. Maybe for B, QH will be 2000 minus 2000 by 1000 plus QL 750 by 100. So entropy change of universe for B, it will be 5.5. So it is greater than 0. Okay. So now let us calculate the entropy change for answer B. For B, let me write it here. No, for C. For C, the entropy change of the universe is equal to same thing. QL and QH will be different. So your same thing minus QH by TH plus QL by TL. Cycle will be 0. Now let us substitute the values. Minus QH for the C is 6000 by 1000 plus 500 by 100. So this will be minus 1. So entropy change of the universe will always be positive. For a reversible case, it will be 0. It will never be negative. Entropy change for a universe will never be negative. So the answer C does not satisfy the entropy principle, but it satisfies the energy principle because the work output is equal to the heat supplied minus heat rejected comes from your energy principle. But entropy principle, it doesn't satisfy. So the answer C is not the right answer. So your right answer will be B. So your answer for this question is B. B is the answer for this question. Maybe now I move to the next question. Question number 2, which of the following statement is false? We know that for an ideal gas, enthalpy for an ideal gas equal to CPT. It is an independent of pressure. So statement A is true. So the statement A is true. Now comes to the B. For a real gas, so here important point here, real gas going through an adiabatic reversible process, so which is isentropic. Reversible adiabatic is isentropic. The process equation given by PV power gamma constant, where P is the pressure, V is the volume, gamma is the ratio of specific heat. So PV power gamma constant for a real gas, so it is valid for a real gas undergoing a isentropic process. Now, if you look at the derivation of PV power gamma, so let me derive it. So this PV power gamma constant comes from the TDS equation. TDS equal to dH minus VdP. TDS equal to du plus PdV. So here entropy constant. So ds will be 0. Then this equation becomes 0 equal to dH. And we assume an ideal gas. So dH equal to Cp dt. It is valid for an ideal gas. So du equal to Cv dt. So with this assumption, so in ideal gas assumption, we derive this equation. So Cp dt minus Vdp 0 Cv dt plus Pdv. So now this equation, you can take it in the other side. Maybe this equation is Cp dt equal to Vdp. This equation minus Cv dt equal to Pdv. So this is equation 1, 2. So 1 divided by 2 gives you minus Cp by Cv equal to Vdp by Pdv. So Cp by Cv is gamma. So maybe you can take it dV by V here and dP by P here. So variable separable. So now if you do the integration, you will get minus gamma ln V is equal to ln P plus a constant ln C. Take it, so maybe you can take it this in this side. Maybe this can be written mathematically ln P plus gamma ln V equal to ln C. So this is the way you can write. Maybe it is a minus ln C because it is a constant. So if you write it, it will be minus ln C. but minus ln c can be taken as a ln constant mathematically. So ln p v power gamma is equal to ln c. This gives you PV power gamma constant. So here important is the ideal gas assumption. So we assume ideal gas. So this will be the false statement because PV power gamma constant is valid for an ideal gas, not for a real gas. So this is false. For an ideal gas undergoing a reversible polytropic process, PV power 1.5 constant. So the equation connecting the pressure, volume and temperature of the gas at any point along the process. So PV equal to MRT. So this equation is nothing but PV equal to MRT. Ideal gas equation. Ideal gas equation. Okay. So polytropic process and ideal gas equation also valid at any point because it is a reversible polytropic process. And ideal gas undergoing. So ideal gas undergoing a reversible polytropic process. So PV equal to MRT is valid for an ideal gas. So this is also true. Any real gas behaves as an ideal gas at sufficiently low pressure and sufficiently high temperature. So this is also true. So the false statement is B. So your answer is B. Okay. So now we move to the next question. Consider a fully adiabatic piston cylinder arrangement. Adiabatic means no heat transfer. So your heat transfer into the piston, into the cylinder will be zero because of adiabatic. The piston is massless. Cross-sectional area of the piston is A. So the area of cross-section of the piston is A. A is the area of cross-section of the piston. Gamma is the specific heat at constant pressure to the ratio of specific heat at constant pressure. Gamma is Cp by Cv. Gamma is Cp by Cv. The piston initially located at a location L1. So this is the initial location L1. L1 is initial. The initial pressure inside the air is P1, which is greater than P0. P0 is the atmospheric pressure. The stopper S1 is immediately removed and the piston moves to the position. So this is the final position. Where the equilibrium pressure of air inside the cylinder is P2. So the pressure changes inside pressure, changes from P1 to P2. So inside pressure changes from P1 to P2. Okay. In the movement of the piston. But what way it is changing, we do not know. P1 to P2 change, whether it is isothermal or polytropic, or what way it change, we do not know. But what is asked is the work done by the piston on the atmosphere. So that means the atmosphere is giving a resistive force. So let's say F is the resistive force. This F, the resistive force will be equal to the atmospheric pressure into the area of the cylinder. So this is the resistive force which is acting on the piston by the atmosphere. So work done by the piston on the atmosphere. So work done by the piston on the atmosphere is equal to the force, the atmospheric pressure acting on the piston into the distance moved. Distance moved is L2 minus L1. So this is the distance moved. So we know that this is P0 into A into L2 minus L1. So your answer is B. For this question. Now we move to the question number 4. So the piston cylinder arrangement shown in the figure has a stop at location. So there is a stop here. Stop here. So the cylinder initially at 140 kPa, maybe this is the initial position. Initial position, so we will take it as 1. So at this initial position, the pressure P1 is 140 kPa and temperature T1 is 350 degrees centigrade. So maybe this, if you write in Kelvin, plus 273. Six 23, 623 Kelvin. So this is the initial position. And now, this from there will be a, so we are removing the heat. The system is now cooled to atmospheric pressure. So that means you are removing the heat. So as you remove the heat, what will happen? The piston will move down and it comes to this stage. So this is the second stage. So this is the second stage, state 2. So it comes to this stage. And we do not know what is this temperature at this stage. T2. We do not know. Because T2 is the temperature, maybe if you continue to remove the heat from 1 to 2, the process, 1 to 2, the process will be pressure constant. Because if you look at that, the piston is freely moving. So whenever the piston is freely moving, the pressure cannot change. Maybe if you take the free body diagram of this piston at the initial position, so massless piston. So you have atmospheric pressure into area acting downward, and you have a inside pressure into area. So maybe this I take it P1 into A. So there is no other variable. The piston is no friction, nothing is mentioned about the friction. Maybe the mass of the piston can be there. The system is now, because mass of the piston can come here. So since the mass of the piston is constant, atmospheric pressure also constant, because mass of the piston as well as the atmospheric pressure is balancing the P1 into A. So that means if the piston is, if you remove the heat, the piston will move down freely without changing the constant pressure. So that means from 1 to 2, the process will be pressure constant. And the final temperature will be 25 degree. So we do not know. This 25 degree means maybe further it can go to process 2 to 3, but during this time the volume will be constant, because below the point 2, the piston cannot move down because the cylinder is stopper is there. So we have to check whether this T2 is 25 degree. If the T2 is 25 degree, then 1 to 2 is the heat transfer happens only in the constant pressure process, but we do not know. We need to understand what is the value of T2. So you take the pressure constant process for which, so when the pressure constant process, we know that the ratio of volume V1 by V2 is equal to the ratio of temperature V1 by V2. So we know that V1 is area of the piston. A is the area of the piston into 3. Length into 3. V2 is the area of the piston into 2. So V1 by V2 is, so we know that T1 by T2 equal to maybe V1 by V2 3 by 2, 1.5. So T2 is equal to T1 by 1.5. T1 is 620, should not substitute in degree, it must be in Kelvin. So now let's see what is that. 415.33 Kelvin. So this will be how much degree centigrade? Minus 273. 142.33 degree centigrade. That means, so as you remove the heat from the process 1 to 2, the temperature reaches 142.33 degree when the piston just touches the stopper. So that means you are continuously removing the heat. So heat will be removed from 1 to 3. So the total heat transfer. So this will be heat removal 1 to 2 pressure constant plus heat removal in 2 to 3 volume constant, because 2 to 3 is volume constant and the temperature at 3 is reaching 25 degree, because this will be 142.33 degrees centigrade from there. So what is asked is what is the absolute value of specific work done during the process. So work done happens only constant pressure process. So we know that work done is integral PdV. So for pressure constant process, so the work done, which is 1 to 2, is equal to the pressure is constant, so V2 minus V1. And we know that from the ideal gas equation, PV is equal to P, maybe because it is asked kilojoule per kilogram. So we take its specific volume is equal to RT. So this will be, maybe you can write as R into T2 minus T1 from the ideal gas equation. So work done during volume constant process, work done in the process 2 to 3, volume constant. So 2 to 3, it will be 0 because integral PdV will be 0. So it's a closed system. So work transfer in a closed system. Piston and cylinder assembly is a closed system. So only for closed system, the work transfer will be integral PdV. So So now you can substitute. You know that temperature T2 minus T1, R is maybe kilojoule per kilogram. So you can even substitute this in 0.287 into T2. T2 will be maybe temperature difference. So when you have temperature difference, then you can substitute degree centigrade or Kelvin. Temperature difference in degree centigrade or Kelvin will remain the same. So we can substitute T2 is 142.33 minus T1 is 350. 350. So this work transfer will be equal to so minus 59.6 kilojoule per kilogram. Because if you see that you are substituting this R in kilojoule per kilogram Kelvin, and this temperature difference is in degree centigrade or Kelvin, doesn't matter. So same will be the same. So this unit, Kelvin and Kelvin will be getting cancelled. So you get an unit of kilojoule per kilogram. So unit is important. So the answer, but constant volume process, the heat transfer will be, work transfer will be 0. So the answer is equal to maybe sign we can, the negative sign indicates that the work is given into the system. So you are giving a work during the process 1 to 2, which will be minus 59.6 kilojoule per kilogram. Negative sign indicates the work is given into the system. So we want only the magnitude, absolute value of specific work done. So it is 59.6 kilojoule per kilogram. So if you are asked to find out the heat transfer, then you have both in the process 1 to 2 as well as process 2 to 3, you have heat transfer. Maybe we will just try whether we can calculate the heat transfer. So I just go to the next slide. So there will be process 1 to 2. So this is the pressure constant process. So heat transfer. So this will be work transfer in the process 1 to 2 plus change in internal energy. Okay, so this is the, so here heat in is positive, out of the system is negative. So sign convention you should follow when you apply this equation. This is the first law of thermodynamics. First law of thermodynamics applied to closed system or a process 1 to 2. Okay. So when work transfer is out, then it is positive. Work is in, then it is negative. Okay, so this is the understanding you must have. So we want Q1 to 2. So work, if you look at that, the work is given into the system, so negative. Minus, maybe we want everything in kilojoule per kilogram. So then accordingly you can substitute. So minus 59.6. This is in unit, must be careful. Then this will be CV into the temperature difference, T2 minus T1. So now we can substitute all values. CV, CP is 1.005 kilojoule per kilogram Kelvin. So this CP, CV value for air. So this is air, right? So you can just see it is a piston cylinder arrangement, air. So it contains air. Air. So CV is this value is 0.718 kilojoule per kilogram Kelvin. CP minus CV is R. 0.0718. So R is your CP minus CV. 28.287 kilojoule per kilogram Kelvin. Since we wanted it in kilojoule per kilogram, so accordingly we can substitute 6. Because for an ideal gas, we know that ideal gas change in internal energy is equal to maybe m CV into the temperature difference. But here per kg mass, so we take it CV into T2 minus T1. CV is 0.718. T2 is the temperature. If you see T2 is maybe temperature difference, you can substitute in degree centigrade 142.33. T2 is 142.33 minus 350. Okay, 142.33 minus 350 is your T1. This is the T2, T1. Let's see how much we are getting. So definitely it will be minus because the heat is going out of the system. So whenever you have temperature difference, it doesn't matter. You substitute in Kelvin or degree centigrade. Minus 208.7 kilojoule per kilogram. So the negative sign indicates that heat is going out of the system. Now for process 2 to 3, it is volume constant. Same, but for a process 2 to 3, internal energy change. So work transfer will be 0 for constant volume process. So 2 3 will be equal to, this will be CV into the temperature difference, T2 minus T1. So here it is T 3 minus 2. 3 minus 2. Okay, so not 1 to 2. It is 3 minus 2. So you should be very careful about this. This kind of small careless mistake will reduce your mark. T3. T3, let's go and see T3. T3 is 25. T2 is 142.33. 25. minus 142.33. So let's see. So this also will be negative because you are losing the heat is removed from the system. So it will be minus, because this is substituted in kilojoule per kilogram Kelvin. This will be in degree centigrade. So anyway, temperature difference. So you'll get kilojoule per kilogram. 84.24 kilojoule per kilogram. So the total heat removed. So total heat removed is Q1 to 3 is equal to Q1 to 2 plus Q2 to 3. Q1 to 2 is minus 208.7. Q2 to 2 minus. Negative sign indicates the heat is going out of the system. Minus 292.94. Okay, so this is the answer for total heat removed, 292.94. Maybe this is not asked. Maybe what is asked is the only work transfer, specific work done during the process. But maybe we just extended this problem for finding the heat transfer also. So now we go to the next question. So a heat pump is driven by work output of a heat engine. So there will be a work output which will be supplied to the heat pump. So the work output will be equal to the work input to the heat pump. Maybe this we will take it T1. So this we take it Q1. Q1 is your 150 kilojoule, and there will be a heat rejection Q2 with the temperature T2. So now we are taking this we take it T3. There are 3 reservoirs. Anyway, heat pump and refrigerator will operate from low temperature to higher temperature. So the flow direction will be from low temperature to higher temperature for heat pump and refrigerator. For heat engine, it will be from a higher temperature to low temperature. And this we take it Q3, heat it is taken from there, and maybe this is Q2 dash. Let's say Q2 dash is given to the room temperature. So now the combined system to be ideal. Ideal system means Carnot. Only Carnot system will be considered as an ideal system. The total amount of heat delivered to the room together by the heat engine and the heat pump. So what is this Q2 plus Q2 dash? This is what is asked. This is the total heat which is delivered to the room. So now we know that the efficiency of heat engine. Now ideal. So that means this is a Carnot engine. This is the Carnot heat engine. This is the Carnot heat pump. Carnot heat engine and Carnot heat pump. Because of the word ideal, because ideal means it must be a Carnot heat engine and Carnot. So efficiency of this heat engine is T1 minus T2 by T1, which you can write as heat supplied minus heat rejected by heat supplied. So now from this you can get to the Q2. So T1 is 1000 minus T2 is 300 by, because it is a Carnot heat engine, that is why this T1 minus T2 by T1 equal to Q1 minus Q2 by Q1. Otherwise it will not. Because of the Carnot engine, these two are same. With 1000 is equal to 150. Maybe in terms of kilojoule is what is asked in kilojoule. So we write in kilojoule 150 minus Q2 by 150. So let's find Q2. So my 45 kilojoule is the heat released by the heat engine to the room. So heat pump. So now come to the heat pump. Here we write COP of heat pump. So for cycle it is efficiency. For heat pump it is COP. So it is a Carnot heat pump. So it is the higher temperature T2 minus T3. Okay, so heat pump, the COP will be higher temperature by higher temperature minus lower temperature. So this you can write in the same way. Here it is heat given to the high temperature desired effect Q2 dash by maybe work input. We write work input. So this work input, if you look at, so the work from the diagram, so the work output is what is given as the work input. So what is work output? Q1 minus Q2 is your work input. Q1 minus Q2. Q1 is 150 minus Q2 is 45 is the work input. So this will be 105. 105 kilojoule is the work input to the COP, to the heat pump. So now you can substitute the value T2 is 300 by 300 minus 280 is Q2 dash by W in 105. So you get Q2 dash, because we substituted this work input in kilojoule. So you get Q2 dash also in kilojoule. So 1575 kilojoule. So the total heat delivered to the room by heat engine and the heat pump. So maybe here you can sum it both. Q2 is 45 plus 1575. So together 1620 kilojoule. So your answer is 1620 kilojoule. So this is the answer for this. So now we move to the next question. So under steady state condition, a superheated steam enters the turbine with an enthalpy. So you have a turbine. So it is the entry to the turbine. This is the exit to the turbine. Entry state we will take it 1, exit state we will take it 2. So this will give, turbine will give you work output. Okay. So under steady state condition, it enters the turbine with an enthalpy, maybe H1. 3200 kilojoule per kilogram. And wet steam leaves the turbine at a pressure. Maybe it leaves at a pressure P2, 0.1 bar pressure, and maybe enthalpy H2. So the heat loss, so there is a heat loss. Hundred kilojoule per kilogram. Work output 1000 kilojoule per kilogram. Kinetic and potential energy for inflow and outflow are neglected. So at the pressure 0.1, you are given, so at pressure 0.1. So at this pressure, you are given saturated liquid enthalpy. So that is HF, 200 kilojoule per kilogram. Enthalpy of vaporization. Enthalpy of vaporization is change, the phase change enthalpy. Liquid to solid, liquid to gas. So HFC is 2400 kilojoule per kilogram. So everything is there in kilojoule per kilogram. So we follow the same unit. So what is the dryness fraction of the steam at the exit? So what is X2? Because it is a wet steam, so you have a dryness fraction. So now we apply the steady flow energy equation. Steady flow energy equation. That is energy in equal to energy out. So energy in along with the mass flow. So mass flow we are taking 1 kg per. So enthalpy may be kinetic energy and potential energy. Okay, so this, let us write everything together, and then this is the energy going in and no other energy which is going into the system. Then energy going out, definitely enthalpy H2, V2 squared by 2 plus G is at 2. Then heat is going out, so heat loss. Then work is going out. And we know that the kinetic energy and potential energy are neglected. So this will be 0, this will be 0, this will be 0, this will be 0. So now enthalpy H1, we substitute in kilojoule per kilogram is equal to H2, we don't know. Heat loss 100. Here you need not to follow the sign convention. So energy going in will be taken one side, energy going out will be taken in the other side. So sign convention is not a big issue here. Then work output 1000. So we take H2. Two thousand hundred kilojoule per kilogram. H2. And H2, it is the wet steam. So it is a wet steam. So this is the wet steam. So we can write for wet stream, it is HF plus X at state 2. So H2 is known, HF is 200 plus X is X2, HFG is 2400. So we can get X2. Point 79. So it is rounded off to 2 decimal. So this will be the answer. So your dryness fraction will be 0.79. The answer. So now we completed the problems from the thermodynamics. So now thank you for watching this video. If you are happy with this video, please subscribe the channel and share this video to your friends who are preparing for GATE mechanical engineering subject. So if you want to join for GATE 2026 video course, please contact in the number. There are 2 mobile number and you have a website address. So you can join. Thank you.